Hello everyone. In this talk, we will explore the world of neuromorphic computing. We will examine how this innovative field is inspired from the human brain to improve computing and how the contribution of Intel Labs benefited the advancement of neuromorphic computing. We will discuss about the contribution of Intel Labs in the later part in this talk. For now, we will discuss the concept of neuromorphic computing. The human brain is capable of extraordinary information processing with remarkable efficiency. This incredible efficiency is what neuromorphic computing aims to replicate in machines. The basic idea of neuromorphic computing is to develop a chip that emulates the functions of the human brain. Neuromorphic architecture are based on the brain neocortex, where advanced functions like sensory perception, commands, and language are assumed to take place. The neocortex layered structure and complicated connectivity are important to its ability to process complicated information and enable human thinking. The neocortex is made up of neurons and synapses that send and receive information from the human brain with extraordinary speed and incredible efficiency. Neuromorphic computers aims to duplicate that efficiency. They do this by forming what are called spiking neural networks. These are formed when spiking neurons, which hold data as if the biological neurons, are linked together via artificial synaptic devices that transfer electrical signals between them. A spiking neural network is the hardware equivalent of an artificial neural network, which is a collection of algorithms run on a regular computer that mimics the logic of how a human brain thinks. If we compare traditional computers and neuromorphic computers, traditional computers have reached their limits since they think in binary. Everything is 1 or 0, yes or no. You only have two options. So the programming we employ and the question we ask this machine must be very specific. Neuromorphic computing is a bit more flexible. Instead of utilizing an electrical signal to represent 1 or 0, the makers of this new chip seek to make their computer neurons communicate in the same way as biological neurons do. This requires a precise electric current that passes across the space between neurons. Depending on the number and type of ion, the receiving computer neurons are engaged in the same way, giving you far more computational alternative than just yes or no. This ability to transmit a gradient of understanding from neuron to neuron and to have them all functioning together simultaneously means that neuromorphic chip could eventually be more energy efficient than our traditional computers, especially for high complicated tasks. Conventional CPU operates dramatically different way from the way the actual brain works. About 99% of all chips are designed with a clock. This is what is called synchronous design methodology. It is continually reading a rigid sequential instruction set, which is inspired more directly from how the brain works. With neuromorphic chips, we're creating a huge parallel sea of neurons where each one operates without any prescribed order. With its many advantages, neuromorphic computing is a revolutionary advancement in the field of high performance computing. Neuromorphic computers aim to be faster than traditional computers by mimicking the brain. They use artificial neurons that process information simultaneously, unlike the step by step approach of traditional computers. Additionally, these chips only activate relevant data, saving time and energy. Neuromorphic computing shines in pattern recognition due to its brain-like design. With interconnected artificial neurons working together, it can analyze data in parallel, like how our brain spots patterns in image and sounds. Neuromorphic computing excels at energy efficiency by drawing inspiration from the human brain. Traditional computers constantly shuffle data, guzzling power. Neuromorphic systems, on the other hand, employ event driven processing. Neuromorphic computing learning speed is brain inspired. Like how our brain learns, connections between artificial neurons can adjust on the fly based on data. This, combined with processing information in parallel, allows them to learn from the massive data sets and adapt much faster than traditional computers that process information step by step. If we look into the challenges, the difficulty of maintaining computational nodes is another important aspect of neural computing. Conduction switches in transistors are typically the nodes of bit computation. However, the cost of using a generalized alternative way to achieve non-bit computing is that formal neural computing requires computational nodes like neurons. This indicates that artificial synapses and stimulation require development. The high manufacturing process and technological cost leading to low production efficiency are the cause of the low simulation efficiency. There are still many problems in the research of new materials for the neuromorphic hardware. In the future, researchers in the neuromorphic disciplines consider new materials belonging to neuromorphic computing can be found in place of transistors to new hardware design. The latest insights of neuroscience are being applied to computer architecture to transform computational technologies from the bottom up. Over time, we will see neuromorphic chips deployed in a wider range of real world applications.
In the current trend, there are many competitions and collaborations to get advanced in neuromorphic computing, such as IBM, which made Spinnaker, Qualcomm's Zeroth, Samsung's latest chipsets. In the list, there is Intel, which leads in neuromorphic computing due to their advanced Loihi chip series. In March 2018, Intel released Loihi for public use with launching of its Intel Neuromorphic Research Community. This program, which now numbers over 100 research groups around the world, has led to a growing body of quantitative results that confirms both the value and novelty of neuromorphic architectures and algorithms compared to von Neumann solutions. The result point to a niche for a neuromorphic chips that is different and more general than prevailing conventional view. Loihi incorporated self-learning capabilities, novel neuron models, asynchronous spike-based communication, fine-grained parallel computation, and many other properties inspired from neuroscience modeling with leading silicon integration scale and circuit speeds. Loihi can execute certain demanding workload up to 1000 times faster and 10,000 times efficiently than conventional processors. Over the past few years, Intel NRC members have evaluated Loihi in a wide range of application demonstrations. Some examples include adaptive robot arm control, visual tactile sensory perception, learning and recognizing new odors and gestures, drone motor control with state-of-art latency in response to visual input. In most of these demonstrations, Loihi consumes far less than 1 watt of power, compared to tens to hundreds of watts that standard CPU and GPU solutions consume. These are some systems developed by Loihi. Kapoho Bay is a USB stick-based system that comprises two Loihi chips with 262,000 neurons and support all kinds of real-time edge workloads. Nuhuku is a baseboard that incorporates 8 to 32 Loihi chips used as a framework to build very large systems. The Nuhuku board with 32 Loihis support up to 4 million neurons and 4 billion synapses. Pohoiki Spring is Intel's largest rack-mounted neuromorphic system, integrating 24 Nuhuku boards for a total of 768 Loihi chips, 100 million neurons and 99 billion synapses, while operating at a power level of under 500 volts. Building on the insights gained from the research performed on the Loihi chip, Intel Labs introduces Loihi 2. Loihi 2 is Intel's second-generation neuromorphic research chip, featuring a massively parallel interconnect of fully asynchronous digital neuromorphic cores that communicates partially using spike messaging. Unlike Loihi and many other existing neuromorphic processors, Loihi 2 supports integer-valued spikes, the graded spikes, along with the usual binary spikes at an insignificant additional energy cost. Each Loihi 2 Neuromorphic core or neurocore offers support for a wide variety of common synaptic connectivity topologies such as dense, sparse, convolution, as well as less common ones such as factorized or stochastic connections. Each neurocore can have up to 8,190 neuron computation node, which are programmable using flexible microcode programmable neural engine to describe a multitude of neuron computation dynamics and spike mechanisms. Loihi 2 has the same base architecture as its predecessor Loihi, but comes with several improvements to extend its functionality, improve its flexibility, increase its capacity, accelerate its performance, and make it easier to both scale and integrate into larger systems. Each Loihi 2 chip consists of microprocessor cores and up to 128 fully asynchronous neuron cores connected by a network on chip. The neuron cores are optimized for neuromorphic workloads, each implementing a group of spiking neurons, including all synapses connecting to the neurons. All communication between neuron cores is in the form of spike messages. The number of embedded microprocessor cores has doubled from 3 in Loihi to 6 in Loihi 2. Microprocessor cores are optimized for spike-based communication and execute standard C code to assist with data input-output as well as network configuration, management, and monitoring. Parallel input-output interfaces extend to on-chip mesh across multiple chip up to 16,384 with direct pin-to-pin wiring between neighbors.